All right, so for section 4-5, we have one more postulate for congruent triangles. So yesterday we had SSS, side, side, side. SAS, side, angle's the included angle. And then SAS, did I just say that? ASA, where the side is now included. So those are your three. Then, today, we're going to have AAS. This one's an actual theorem, where the other ones are postulates. If you call this a postulate, I'm not going to mark you wrong. I'm not going to make you go crazy as to whether it's a theorem or a postulate. But it's angle, angle, side. This is different than ASA. ASA has the side included. Angle, angle, side, the side is not included between the two angles. It's the unincluded side. So there's actually two different sides you could choose for AAS. I'll show you here in a minute. I did draw a picture to go with it. I did note below here at the bottom in red for a very good reason. Remember yesterday we talked about SSF or SSA as a bad word spelled backwards. Side side angle. You cannot prove angles congruent with a bad word spelled backwards or forwards. So if you're trying to prove a triangle congruent with two sides and an angle, it better be the included angle rather than the unincluded angle. If you want to see the reason for that, look on page 215 and 216 in your textbook. Example 2 will give you an explanation if you're dying to know. Melissa, did you get a target sheet? So if you look at the picture of the two triangles that I have up here, pick any two angles in your triangles that are corresponding. So I just happen to pick A and D and C and F. So if those are my two angles, don't I have two possible choices for a non-included side? Remember the included side, what would have been the included side on this triangle here? AC would have been the included side. That means that the other two sides are not included. So couldn't I have chosen AB or BC as a non-included side? I could have. I have two choices. Whereas before, you've only had one choice. So I happen to choose AB, and then DE is its corresponding non-included side. So when you're asked, let's just say that you were given these two angles, these two sets of angles are congruent, and you have to tell me what other side that you would have to prove congruent for AAS, then you have two answer choices. You could tell me that AB has to be congruent to DE, or you could have told me that BC is congruent to EF. So this is one of the possibilities where you have two choices, and I'll show you what I mean in a minute on our next example. But look at this. If I have a set length here, Can't change this length, can't lengthen it, can't shorten it. And I have a set angle here. So that means that I have a line that could go out here infinitely in this direction. And I have another set angle here. If I take that set angle here and I start bringing it towards this line right there until I can combine it with this line to have that angle and create a triangle, there is no way I can't open this up at all, right? There's only one way that I could put an angle here and make a triangle here by moving this closer and closer until finally I get it to work. And then this will be a specific length and that'll be a specific length. There's only one way that I can do that if these angles are set that can't move. I can't draw any other type of triangle. All right, so let's look at some examples. So here's an example of a picture. You don't have to write these down. But here's two different sets of triangles. One triangle shares one set of triangles, they share a side. The other set of triangles don't. And look at their arc marks and tick marks. You're going to be given this and have to decide, is this SSS? Is it ASA? Is it SAS? Is it AAS? So I'll give you a picture like this, and you kind of have to decipher what's going on. Sometimes this is a little hard for some of you to see, but if these are my two angles, if you follow the angles with your finger, don't you see the line that I'm tracing? Wouldn't this side right here be the included side? Yes or no? So since that's the included side, it can't be ASA, because that's not the side that they chose, right? If you follow the triangle in a circle, starting at one of the angles that are marked, would you have angle, then you come to angle, then you come to side, right? Or if you followed here, you come side, angle, angle. Well, over here, I have absolutely no tick marks marked, right, on the second one. But what can you assume is congruent? On this picture, what can you assume is congruent? What side length? KM, why? They share a side. So you might have a picture where they don't give you all the information because you're supposed to be intuitive and figure that out on your own. So then you would have to make that mark in there yourself, and then again you could start on one triangle and follow it one vertex with your finger. Okay, I've got side, then I hit an angle, then I hit an angle again. So side, angle, angle, which is the same as angle, angle, side, right? So that's one of the things you're going to have to do is decipher from the picture what type of postulate that they're talking about. Then I want you to write this down. So we're going to look at a proof. Yay. Write down the picture, given, the proof statement, and your statement and reasons columns. Do these two triangles share a side? The way it's drawn, do they share a side? No, right? They're overlapping on part of the sides, but we cannot conclude that BC is congruent to XZ because the full side is not shared. we about ready to start? So let's look at what they gave us, and they've marked part of the picture for you, but part of the picture they haven't. Whatever is in the given, you need to mark the picture with that. So they told you that angle A is congruent to angle Y, and so they put single arc marks up here. Great. Then they said angle ACB. Why are they all of a sudden calling the angles with 3 letters now instead of 1? ACB. Could there be some confusion if we said angle C? It's possible. There's really only one angle associated with C here, isn't there? It could be here though, right? So that's why they're not calling this angle C. So now you have ACB, which is this angle here, and then YXZ, which is this angle there. So they gave those appropriate double arc marks. So we know it's angle. The question is it angle side angle, or is it going to be angle side? Are we going to have an included side or non-included side? And then look at the third piece that they give you. BX from here to here is congruent to ZC from here to here. Just those pieces. That's not a full side of any of the triangles, is it? Nope. What segment do the triangles share in common? XC, right? You're going to see that coming into play in the proof. All right, so I'm going to give you the statements one at a time. What's your theory as to how we're going to prove the triangles are congruent? What do you think we could do? Just given the information. What do you think we should try to prove is congruent for our third part? Because currently we have an A here and an A here, right? And this isn't exactly a side. What side do you think on the triangle we might prove congruent? Because there's no way I can prove, well, there's no proof for AAA. In fact, you cannot prove triangles congruent with AAA. So even though I know that the third angle, angle Z and angle B must be congruent, we're not going to prove an angle, so it has to be a side. Jade? The XC is going to come into play, but it's not the full side of the triangle. So I'm going to have to prove that BC is congruent to XZ. If this part is congruent and this part is congruent, and they share that part, doesn't it seem reasonable that these sides would be congruent? Somehow we have to prove that. And you're going to see us using the segment addition postulate to do that. So watch how it happens. All right, so here's our first. Here's our first statement. And next to that first statement, if I were you, which means that if I'm going to prove, by the way, this angle, and this whole side here congruent, isn't that angle, side? So I'm going to prove these triangles congruent with angle, side, because that side, BC, is not included or in between angles A and C. So it's the non-included side, AAS. So notice here that angle A is congruent to angle Y is an angle statement. And then angle ACB is congruent to angle YXZ is an angle statement. So I have angle right now. Those are straightforward congruent statements. All I have to do is prove a side congruent, and I can prove the triangle is congruent. It's going to take us a little bit to get there, though. Where do we get this statement? Given. So good. All right, so then the next, then we go to, what's that notation saying? XC is equal to XC with nothing above or in front. The measure of XC is equal to the measure of XC. That's what it's saying. XC equals XC. What's the reason for that? Reflexive property, very good. And the reason why we're putting this into the proof is we've got to get it into the proof. We've got to get XC into the proof and prove that it's congruent to itself, because we're going to use it in our angle addition postulate. And so our reason, reflexive property of equality, or reflexive property of congruent segments, although they didn't use segment notation here. Then notice that we have the difference in notation going from BX, segment BX is congruent to segment ZC, and then we just have BX is equal to ZC. Remember what the reason for that was? To change in notation? Definition of? No, definition of what? I don't think I heard it properly. Congruent segments? It should be definition of congruent segments. Remember, that is your change in notation reason. Oh, goodness, I keep giving you the answers ahead of time. Bad me. What do you know about the distance from B to C? What's it made up of? What segments is B to C made up of? BX and XC. BX and XC, right? And what's this distance from X to Z made up of? XC and CZ, right? CZ and XC. There's a reason why we brought those in there. Now look what our next statement is. We have BX plus XC, and we're saying that that's exactly equal to XC plus CZ. Here's the XC and XC right here from this statement here, right? Didn't we basically take two equal parts and add them to both sides of the statement? Isn't that what we did? And it created each of the halves. Isn't that your segment addition postulate? But look at what the reason is. Why is it the addition property and not the segment addition postulate? If I had just this, what would that have been? Well, if I had had this, BX plus XC is equal to what? BC. That would have been your segment addition postulate. But again, we have to look at what came above. Since we started with this, and then they told you that these are congruent pieces, they look different, but they're both congruent, then I can add each one of these to each of these sides. And I've added the same thing to both sides. That's your addition property of equality. So now I have BX plus XC. That's the full length of this triangle, isn't it? And XC plus CZ is the full length of this triangle. So what you're going to see happening is we're going to replace this with some values here. Now we've got this is equal to BC and this is equal to XZ. What is that? That's your segment addition postulate, right? So that's the difference between 4 and 5. Why do you think they did that? What do you know about BC and XZ? What do you know about BC and XC? Yeah, right here and right here. Aren't they congruent to each other? So since you've already said up here that they're congruent pieces, what do you think is next? Oh, this is your segment addition postulate. So sorry. Oh, I'm sorry, we didn't have it up here. But these pieces right here are equal, right? These are the ones that correlate. So now, if these pieces are equal, and each of these pieces from here are equal to BC and XZ, then doesn't it stand to reason that BC is congruent to XZ? Right? What do you think the reason is? This is equal to this, and this piece is equal to this, and this piece is equal to this. So now those pieces are equal. It is not the transitive property, right? It is the substitution property, because all we're doing is substituting one thing for another. Now, most of you would be happy and say, okay, I've shown that side BC is congruent to side XZ, but have I used a congruent symbol? Have I used a congruent symbol? No. I've used an equality symbol. So you're going to see a change in notation. Isn't that your definition of congruent segments again? The only difference from 6 to 7 is your change in notation. So our reason is definition of congruent segments. Now that I have that, remember here was my A. Here was my A. Finally, it took me all that time to get down to my S. The minute I hit that third piece of AAS, what can I do? I can put my proof statement, right? And what's my reason for the triangles being congruent? What? AAS. Done. I probably wouldn't make you on a test do this specific proof all by yourself. What I might do is put all the statements up there, or some of the statements and some of the reasons, and have you fill in the difference. But nothing in here has been new, has it? Other than the AAS? Haven't we used these reasons before in the past? You should start to become familiar with them. And it shouldn't be quite so foreign. All right, let's talk about homework.